Log on, tune in, find out. Another good idea from Cambridge.
Anuj Dawar from here, Cambridge. He is a program participant of our program, but I think I should also mention that he was the principal organizer of the 2006 program called Logic and Algorithms, so he was in my position back then. He has been a great inspiration for us because he guided us through some of the early stages of writing the proposal and negotiating with the Newton Institute. Today he represents theoretical computer science, and he will give a presentation on syntactic and semantic complexity classes, which fits very nicely with the title of the program.
Well, yes. Actually, first, before I start, let me just say, I realize that this is a wide-ranging audience, wide in terms of backgrounds. So please do feel free to interrupt me at any point if there's something which I haven't defined, which is not clear, or anything which you want me to expand on. I'm interruptible at any point. So let me start with thanking the organizers for the invitation to speak here. When I was first asked to speak, I think Benedict wrote to me and asked if I would speak about applications of computability theory in theoretical computer science, which seemed like a very broad remit to work from. Pretty much all of theoretical computer science would fall in there. So I took inspiration from the title of the program, which is Semantics and Syntax, and I thought I would talk about, this is one particular stream where this distinction between syntax and semantics comes up in complexity theory, that is in computational complexity theory. So it's one particular meaning of the distinction between syntax and semantics. It's quite common in complexity theory. People often refer to complexity classes as being either syntactic or semantic. And this is not a sort of mathematically precise statement, but I want to elaborate on what this distinction means. And I'm going to tie it in to my favorite open problem from descriptive complexity theory. So that's the theme of this talk. So as a guiding principle, this is again looking at the program description for this Newton Institute program, and I think Benedict mentioned this in his opening remarks this morning. Syntax we understand vaguely as symbolic manipulation, semantics as interpreted mathematical structure of some sort. And to my mind, the notion of computability, Turing's notion of computability, essentially elucidates the question of when can semantics be reduced to syntax, right? When can we find a syntactic way of dealing with semantics, okay? And this is the question I want to sort of explore in the context of looking at complexity classes. And I'm going to motivate this question, as I said, by tying it to one of my favorite problems from descriptive complexity theory. What's my favorite problem? It's in some sense the major open problem in descriptive complexity, and one which I've worked on in one way or another ever since I was a PhD student 20 years ago. So complexity theory, as a bit of background, complexity theory is about studying the computational complexity of algorithmic problems. And computational complexity is usually quantified in terms of some kind of resources on some kind of machine model of computation, right? So we have a decision problem and we want to classify it according to what resources are required for its solution on some machine model of computation. And the standard, most famous examples of complexity classes, P and NP, so are defined as P, the language is decidable by a deterministic Turing machine running in polynomial time. So the resource is running time. We limit to polynomials, and the machine model is deterministic Turing machines. NP is those languages decidable by a non-deterministic Turing machine running in polynomial time. So a non-deterministic Turing machine, there are alternative characterizations. You could look at it as deterministic Turing machines with which run in polynomial time with a witness and so on. Okay, we will look at a few more complexity classes in the course of this lecture, but I thought I would start with what I hope is familiar ground for everyone. But as I said, if it's not, feel free to interrupt. Okay, so descriptive complexity, perhaps little less known, provides an alternative syntactic perspective on computational complexity, in that it looks at the complexity of describing certain problems in formal language. So let's start with some examples. Okay, the kinds of decision problems one wants to solve in algorithmically. Let's say talking about graphs. You have an input, a graph, and I want to know, is the graph connected? Okay, this is a decision problem. It's a fairly computationally easy one, certainly polynomial time algorithms. Here's another one. I'm given a graph, and I ask, is it three colorable? Okay, so that is there a way of assigning colors red, blue, and green to the vertices of the graph so that the endpoints of every edge have distinct colors? Okay, that's three coloring, and as you may well know, this problem is NP complete. We don't know whether or not there's a polynomial time algorithm, deterministic one, that does it, but there's a non-deterministic algorithm. And what the non-deterministic algorithm does is, of course, is it just non-deterministically assigns a coloring to every vertex and then checks whether that's a valid coloring. This has an accepting computation path if and only if the graph has a three coloring, and that's the definition of acceptance by a non-deterministic machine, right? If there is some computation path of the machine which results in acceptance, then the input is accepted. Hamiltonicity is another classical graph problem which is NP complete. This is given a graph, right? So a set of vertices. So when I say graph, I always mean an undirected graph, so a set of vertices with a symmetric binary relation on it. Given a graph, does it contain a cycle that visits every vertex exactly once? That's a decision problem. It's NP complete as well. Okay, so if we're thinking of graph problems, as I said, I want to look at things like the complexity of describing the graph problem. So let's fix a formal language. Let's start with, say, first order logic. So what do I mean by first order logic? I mean, it's a language for writing down properties of graphs. So I'll have variables which you think of as ranging over the vertices of a graph. I can say that there's an edge between two vertices x and y. I can form Boolean combinations of formulas, as always in first order logic, and I can quantify over these variables, which means quantifying over the vertices of a graph. Okay? Sometimes, in addition to a binary edge relation, I may allow color. Well, actually, I won't in this lecture. Never mind that line. Okay. So here, if I now write down a formula which has no free variables, right, then it's simply a property which is either true or false in a graph. And here's an example which simply says that the graph contains an independent set of size 3, right? No, sorry, it's universally quantified. This defines the class of graphs which do not contain a triangle. It says so on the slide. I should read my own slides. Okay, this says that, right, so it just says for any triple of vertices, it is not the case, sorry, for any triple of vertices, either there's no edge between x and y, or no edge between x and z, or no edge between y and z. Okay, just an example of how I can specify a property of a graph written down as a first order formula. Now, if I confine myself to first order logic, we can show that anything I can define, right, is computationally fairly simple. In other words, any first order formula I can write, if I look at the collection of graphs which satisfy it, it's decidable in polynomial time and even logarithmic space. Okay, so that's not very difficult to show. I'm not going to run through a proof sketch. Just let's take that as given. And in fact, none of the properties I listed on my previous slide, connectedness, three coloring, and Hamiltonicity, are definable in first order logic. And I want to stress here, okay, because I say everything that's definable is in polynomial time, it immediately follows that three coloring and Hamiltonicity are unlikely to be definable, in that if they were, we would know that P equals NP. But I'm claiming something stronger. We can prove they're not definable in first order logic, right? And in complexity theory, actual impossibility results are hard to come by, in that the real things we'd like to prove, like three coloring is not in P, we don't know how to do. So this is useful. First order logic is weak enough that we can prove real impossibility, undefinability results for it. Okay, and connectedness also, which was my first example, is not definable in first order logic. One can prove this. Now, if you go to second order logic, the second order logic of graphs, of finite graphs that is, we allow ourselves, what does that mean? We extend the rules of first order logic I had before. I now have variables which range over relations on the graph. So I can allow myself atomic formula of the form, a tuple of terms T1 to TA. I mean, in the language I've been defined, the only terms are just variables, so these may as well be just first order variables, are in the relation X. And I allow myself to quantify over these relations, so I can say there is a relation X such that phi, and for every relation X, phi. And now, certainly, all the examples I had become definable. They're all definable in second order logic. They're all second order properties of graphs. I mean, to say that a graph is connected, what do you say? You say for every vertex X, and any set which includes X, any set of vertices X which includes X and is closed under the edge relation includes the whole graph. Okay, that would say that the graph is connected. For instance, I think I have one example on a slide, 3 colorability. How do you say a graph is 3 colorable? You say there are 3 sets, let's call them red, blue, and green. Every vertex in the graph belongs to one of them. No vertex belongs to 2 of them. And for every pair of vertices, if there's an edge, then the 2 endpoints are not the same color, right? Just what you would expect if I asked you to write down a formula, this is the first thing you would come up with, right? So 3 colorability is expressible. And in fact, I mean, I claim here every NP complete problem is expressible, but there is something a bit more. And this is a theorem due to Ron Fagan back in 1974. The notion of NP completeness back then was a relatively new concept. This was just a year or 2 after Steve Cook had proved that satisfiability of Boolean formulas was NP complete, and Karp had followed up with his list of 21 graph problems which he proved were NP complete. And Fagan proved, I've stated this in terms of class of graphs. His formulation is somewhat more general. It's for any class of finite relational structures. But for simplicity, I'll just talk about graphs. So a class of graphs is definable in existential second order logic. So now I restrict second order logic to having only the second order quantifiers, the quantifiers of a relation, are existential only. I disallow universal ones, and so these existential ones appear at the front. If and only if it is in the class NP, right? So if and only if it's decidable by a non-deterministic machine which runs in polynomial time. Okay? This is in some sense considered to be the founding theorem of the subject of descriptive complexity, of trying to characterize computational complexity in terms of, as I said, the complexity of description of the complexity of specifying the problem. And a natural question, well, though it, as you can see, it was a few years before it appeared in published form. Chandra and Harel, in a somewhat different context, studying database query languages, posed the question of whether one can give a similar descriptive characterization for P. That is, a language in which one can define, just say, the polynomial time properties of graphs or not. Okay? They phrase that, does P admit a syntactic characterization? Now, this is, and essentially, the question they posed remains open 30 years on. Does P have a syntactic characterization? I mean, in a sense, if someone came up with a theorem like along these lines, where they gave a syntactic characterization and proved that it was equivalent to P, we would sort of see what that means. But what would it mean to give a negative answer to this question? That's what I want to explore in this talk. I mean, not that I have a negative answer, but what would that actually mean? Right? What does it mean for P not to have a syntactic characterization? Okay. In some sense, this question asks whether we can build P up from below by finitely many operations. think of it this way. First order logic we know is too weak. Second order logic is, in a sense, too much as far as we know, unless P equals NP. So the question is, what can we add? Can we add certain amount of operations, which will be sort of polynomial time computable operations to first order logic, and end up with getting all of polynomial time, right? But we want, in some sense, finitely many operations to make the logic effective. Okay, but as I said, well, like what it says on the bottom line, what I want to ask in this talk is, what would a negative answer to this question mean? Okay, what would it mean to show an impossibility result here? Okay. So we'll start by asking, well, what type of an object is a complexity class? Because if we want to, I mean, as I said, I want to explore this distinction between what complexity classes are syntactic, what is a syntactic complexity class, and what is sometimes called a semantic complexity class. And I'm not going to give you a mathematical definition of what constitutes a syntactic complexity class, simply because I don't have a definition of what constitutes a complexity class, right? Complexity classes, I told you, are defined in terms of machine models, and people come up with different models all the time. I mean, besides the Turing machines, I mentioned, I think, if I go back a little bit, where did I have this? Oh, okay, okay, it's on the next slide. So people define complexity classes in terms of the machine models, which have different kinds of resources, different kinds of bounds, and essentially there's no general rules to the game of what you can define to be a complexity class. But let's start with the basics. Let's say we fix an alphabet of symbols, call them 0 and 1. String for us is a finite sequence of symbols. A language is a set of strings, okay, and that's what our formalization of decision problems usually works as. And a complexity class is a set of languages, okay. So on that grounds, there are obviously the sets of languages. There are lots of them, okay. There are 2 to the continuum many sets of languages. Obviously, not every one of them constitutes a reasonable complexity class. Usually, in particular, we're concerned with countable sets of decidable languages. I say usually, but this is, I mean, people have considered complexity classes which are uncountable, and you know, I'll give you examples of those as well, and so necessarily include undecidable languages and so on. Okay. People define complexity classes, as I said, in terms of a machine model of computation. The kinds of machine models people have looked at: Turing machines. I mentioned deterministic, non-deterministic. You look at random access machines, families of Boolean circuits, interactive protocols, which Nigel mentioned in his talk. All of these you can think of as different models. I mean, all of them, of course, translate into Turing machines. But the point is that they make different kinds of resources explicit. That's the point of having different models. And it's those, in terms of those resources, that one defines then the complexity classes in terms of resources like running time, space, depth, the number of rounds in a protocol, and then one puts bounds on them, whether logarithmic, polynomial, exponential, etc., etc. That's the way complexity classes get defined. And there isn't, you know, I can't give you, as I say, a general theory of what constitutes a complexity class. In fact, some years ago, Scott Aronson, complexity theorist at MIT, says he was trying to solve some problem and discovered that the problem he was working on, well, but 2 obscure complexity classes in the literature which had been proved to have been equivalent, you know, by once he became aware of it, his problem became trivial. So he started compiling a list of known complexity classes, and this has turned into a web page which is known as the Complexity Theory Zoo. This picture is taken from the zoo, by the way, and it currently has 495 entries and counting. And as I said, there is no systematic. I mean, it's a zoo in the sense of it's a zoo without a zoology. I mean, there is no systematic classification of these things. Okay, here are some of the ones that will make an appearance in this talk. So P and NP I've already mentioned. Co-NP, perhaps you know, is the set of languages whose complements are in NP. Okay. BPP, which is usually considered as a formalization of probabilistic polynomial time, or those languages, in other words, which have polynomial time solution by randomized algorithms. I'll give you a definition, a precise definition later in the talk. AC0, which are languages defined by a uniform family of constant depth polynomial size Boolean circuits. This, I'm not going to go into more detail about what this means, but it will serve in this talk as simply a complexity class which is very low in terms of complexity. It's included in everything else, in fact, properly included in everything else we consider. Okay, so it's just a very weak, that's all you really need to know about it. It's computationally a very weak class. So there are 495 entries in Scott Aronson's zoo. On the website, he also has what is called the petting zoo, the zoo of complexity classes which everybody should know about. Well, and this is his picture of the petting zoo. Okay, these are complexity classes which are, shall we say, relatively widely studied. They appear in many different papers. I don't know if it's you can read this at the back, but I'll tell you a little bit. I mean, the lines on this are inclusions. Okay, so there's AC0 right at the bottom. At the top is all, by which just means the set of all languages. Okay, that's certainly one example of an uncountable complexity class. But this is another example of an uncountable complexity class that people actually study. P/poly, it's called. It's those languages which are accepted by a family of Boolean circuits of polynomial size with no requirements on the uniformity of the family. So it can be an uncomputable family. Okay, I'm not going to be concerned anymore with this. I'm going to confine myself to these, which are all classes of decidable languages, so they're all countable classes, right? So they're relatively tame animals in the zoo. But you look at this intricate structure and you realize how little we know about this inclusion structure when I tell you that L and P space are known to be distinct, but none of the inclusions in between them can we say is proper, as far as we know. It's conceivable that NC and P space are the same, right? It's consistent. Sorry?
What is L?
Logarithmic space, right? So L is logarithmic space, P is polynomial space, and we can use a diagonalization argument to separate them. Similarly, we can separate P from X, right? We know that polynomial time and exponential time are distinct complexity classes, right? But in between are lots of things people have considered. I mean, I'll just tell you some of them. NP and co-NP have mentioned. BPP is bounded probabilistic polynomial time. This is, as I said, a nice formalization of what it means to compute randomly with polynomial time. It's not known to be included in NP, for instance, though I think most people conjecture that P and BPP are the same these days. Complexity theorists will believe this. This is zero knowledge, by the way. BQP is quantum polynomial time, et cetera, et cetera. Okay, lots of things I'm not going to look at, but I just wanted to tell you. So partly I want to give you the impression of what's in the zoo. Partly I wanted to place AC0 here at the bottom and tell you that we know that AC0 is properly included in L. So right here, that's a proper inclusion. So AC0 is really weaker than everything else we know on this picture. Okay, and as I said, I'm going to now mostly look at these classes and to some extent at BPP, and hopefully we'll be on relatively familiar ground. You don't need to know anything about what AM, MA, these so-called Arthur Merlin games, etc. You don't need to know anything about that. Okay. Now, I'm going to start with asking a basic question about a complexity class. Suppose I have a complexity class C. Can I enumerate its members? Okay. Well, what does it mean to enumerate its members? I'm assuming now we're talking only about classes of decidable languages. So I may as well start with fixing an enumeration of Turing machines. And I write Li, so having fixed an enumeration, so just some Gödel numbering, I write Li for the language accepted by a machine Mi. Okay? An obvious first question is, can I decide the set of I which define a language in this complexity class? And the answer is generally no. I mean, whatever complexity class you pick, Rice's theorem tells us this set's going to be undecidable. It's, I think, pretty much uninteresting. More interesting, perhaps, is can we get a weak index set for this complexity class? Which is, what do I mean by a weak index set? It's a set of indices of machines so that every element in the set gives us a language which is in the complexity class, and for every language in the complexity class, we have an index in the set which gives us that language, right? So it gives us all the languages in the complexity class, but I'm not asking for all those machines which give us languages in this complexity class. I'm just asking for, every language is represented, not necessarily every machine that accepts a language in the class. Okay, I hope the distinction is clear. And now, this is now a question, a sensible question. By sensible question, I mean one for which the answer depends upon which complexity class you pick. Can we enumerate a weak index set for a class C? Given a class C, can we enumerate a weak index set? And this, I want to say, is the first requirement, not the only one, but certainly a first requirement for a class to have to be called a syntactic class. Okay, a syntax for a class is really a notation for writing down members of the class, and it should certainly satisfy this property. Okay. But usually we want something more. We want these members in this index set to actually witness membership in the complexity class. So going back, I could give you a weak index set, say, for the class of polynomial time languages, but the machines that witness, so that would mean that for every element I in my index set, if I look at machine mi, it defines a language which is in polynomial time. But that doesn't guarantee that this machine itself runs in polynomial time. It could be a very inefficient way of deciding this particular language. So just satisfying these requirements is not quite enough. I want more. If I want a syntax for polynomial time, I want that the members I themselves are polynomial time machines. Okay. Well, I can get a syntax for P, an effective syntax for P in this sense. And so let me make clear about what that means. So, as it says, for a syntactic characterization of a complexity class, I want more than just enumerating a weak index set. I want the machines to witness that the language is in C. So for instance, for an effective syntax for P, I can enumerate all pairs MP, where M is a deterministic Turing machine and P is a polynomial, right? This is just standard Gödel numbering. I have a numbering of machines, I have a numbering of all polynomials. I can enumerate all pairs. And now I can let the code of this pair MP as coding, I basically translate it into the Turing machine, which simulates the machine M for Pn steps. In other words, take the machine M, which on input X simulates M, counting the number of steps. If you get to P of n steps, where n is the length of the input, you cut it off and reject if it hasn't reached a decision. So it accepts those strings which are accepted by M within P of n steps, and that's it. Now, this guarantees, and as I said, let I be the range of this function that takes this to that machine. Now, in particular, if you now look at any machine indexed by an element of I, it runs in polynomial time because I simply cut it off after P of n steps. So the language it accepts is in polynomial time. And for every polynomial time language, there is an index in this set that satisfies it, because if there's a polynomial time machine that runs it, take that machine and take a polynomial bigger than its running time, and cutting it off doesn't change anything. Okay. So this is an index set for P, which actually always gives polynomial time machines, and this is what we call an effective syntax for P. Okay. Now you may be wondering, why doesn't this answer the question I asked right at the beginning? And I'll come back to that later. Okay. But this is now the point I want to make here is, while here, what constitutes a weak index set I just defined for any complexity class, right? This is certainly, as I said, a necessary condition for an effective syntax. when I got to giving this definition, I specifically spoke of the class P, because now what constitutes a witness depends upon how you define your complexity class. What resources, what machine model, etc., etc. And that's why I don't have a general definition, because we're sort of stuck in the zoo and we'd have to come up with a different definition for each complexity class. Okay, so while I know what an effective syntax for P would mean, I'm not necessarily giving you a definition of what is an effective syntax for an arbitrary complexity class. Okay, but I think, as I said, I'm trying to tease out the distinction between what constitutes a syntactic class and what isn't. So I'll give you an example of what is not a syntactic class as follows. So NP is also indexed, for instance, I get an effective syntax for it by taking, for instance, the pairs MP, where M is a non-deterministic machine and P is a polynomial, exactly the same way as I did for P. I have an effective syntax for it. But what about NP intersect co-NP? Okay, this is also a well-studied complexity class. Co-NP has an effective syntax, right? I can take the MP, again, as a non-deterministic machine, as a witness for the complement of the language defined by M. But what about NP intersect co-NP? What would be a witness that a language is in the intersection of NP and co-NP? Here's a natural notion of a witness. It's a machine M and a machine M prime. There's something missing here. That should be LM is the complement of LM prime. Okay. A witness is a pair of machines and a polynomial bound, such that, and really there's more missing here. What I mean is the language accepted by the machine M when it's clocked by P, right? That's what I mean by LM, right? And you look at the language accepted by LM prime when it's clocked by P, it should be complementary to LM, okay? So the set of triples satisfying this condition is certainly an index set for this complexity class. And it is a collection of witnesses. The trouble is this is not a recursively enumerable set. In particular, this condition, this condition is what in complexity theory is called a semantic condition, as opposed to a syntactic condition, right? It's not a condition one can look at the triple and decide, right? So it's not enforced by the syntax of the triples. It is a side condition which is semantic, okay? So that's why, as I said, this is common parlance in complexity theory. P and NP are syntactic classes, while NP intersect co-NP is called a semantic class. And it's an open question, not only whether there is an effective syntax in this sense, but even whether there is a weak index set, which as I said is a weaker requirement. Okay. BPP was my other example. So BPP, as I said, is a formalization of those problems which can be solved by randomized polynomial time algorithms. Here's a formal definition. A language L is in BPP if there is a non-deterministic Turing machine M which runs in polynomial time with the following property, that whenever a string is in the language, okay, you look at the computations of this machine on input X. If the string is in the language, then at least, well, more than 2/3 of those computations should result in acceptance. And if the string is not in the language, then fewer than 1/3 of the computations on input X are accepting, right? So now, to change this to NP, you just have to change this to greater than 0 and equal to 0, right? And that's the definition of NP. But this is the definition of BPP. Now, okay, what would a syntax for BPP look like? Well, let's say that a machine M, this is a non-deterministic machine, is well formed if on any input X, it's the case that either less than 1/3 or greater than 2/3 of the computations of M on input X are accepting, right? Note in particular, not every machine is well formed, right? There are machines for which there will be some strings for which the number of accepting computations is in between those two. And those machines are not well formed in the sense that they don't define a language in BPP. There's no notion of the language accepted by that. I mean, even if they run in polynomial time. Okay. So an index set for BPP is simply the collection of pairs, let's say non-deterministic Turing machine and polynomial P, where the machine you get by running M clocked by P is well formed. Okay? That's an index set, but we don't regard this as an effective syntax, again for the reason that checking whether a machine is well formed is an undecidable property. So I can't look at an element of the index set and tell you whether or not this defines a language in BPP. Okay? So the well-formedness condition is undecidable, and once again, it's an open question whether BPP has an enumerable index set. So BPP is a semantic class. The only definition we have requires a semantic condition. We have no syntactic characterization of it. Okay. Now, I want to relate this notion of syntax to complete problems. And for this purpose, I'm going to take the reductions I'm going to take are AC0 reductions in general. Okay? I mean, we have seen all kinds of reducibilities, and the reason why I'm going to look at this is because AC0 was right at the bottom of our complexity hierarchy. It's about the weakest notion of computation we're considering. So we say a language L is AC0 reducible to L2. This is just if there is an AC0 computable function F. I haven't told you what AC0 computable functions are, but just think of this as just very computational, very easy functions. Such that, well, the usual condition, f of x is in L2 if and only if x is in L1. Okay, and we say a language is complete for a complexity class C if it is in the class, and for every L prime in C, that is, of course, we have that L prime is reducible to L. Okay, so it turns out that now NP completeness was defined in, so this is sort of many one reducibility. NP completeness was defined in Karp's 1972 paper in terms of many one polynomial time reducibility. Here I'm considering much weaker notion of computation, but it turns out that all of the standard NP complete problems are still NP complete even under these very weak reductions, under AC0 reductions. Satisfiability, three-colorability, Hamiltonicity, and pretty much any. I mean, you can. I think you can construct counterexamples of. I mean, examples of problems which are NP complete under polynomial time reductions, but not AC0. But I think they're pretty artificial. Okay. Anyway.
I have a problem that's.
Well, it would mean that. So let me see. I'm saying this. I mean, I can't actually think of an example. I don't even know that this has been proved, but it certainly. Okay, what do I know? I know that by a theorem of Agarwal, any two problems which are NP complete under AC0 reductions are what are called AC0 isomorphic. This is generally believed not to be true for any NP complete problems under polynomial time reductions. It was once conjectured, it was known as the Berman-Hartmanis conjecture, that this was true under polynomial time reductions. I think these days most people believe the Berman-Hartmanis conjecture is false, but I don't know that it hasn't actually been disproved. Well, to disprove it, you would have to separate P from NP. But of course, that doesn't tell you. I mean, I'm digressing a bit far from the theme here. My point is that AC0 reductions are much weaker. There are certainly, we don't know that there are any problems in NP that are not NP complete, because even proving that means separating P from NP. We certainly know that there are problems in NP which are not AC0, which are not complete under AC0 reductions, because AC0 is properly weaker than NP. Okay, so but pretty much any natural NP complete problem turns out to be complete under AC0 reductions. That was the essence of what I was trying to say here. And you can find complete problems under AC0 reductions in most of the other complexity classes I've listed up there. Certainly there are p-complete problems, fairly natural ones, under AC0 reductions. Okay, but what I wanted to say is, if I have a complete problem in a complexity class, I can get an effective syntax. Okay, and that's from a fairly general construction. And the idea is, because the AC0 computable functions themselves are enumerable. Okay, I'm not going to tell you why, because I haven't given you a definition of what the AC0 computable functions are. But once you know that, then from a complete problem, you can construct a syntax for the complexity class. The idea is, you take machine mi to the machine that on an input x computes fix, fi being the ith function in this enumeration, and checks whether it is in L, where L is the complete problem. Okay, so the language decided by mi is simply the language which is reduced to L by function number fi in the enumeration of AC0 computable functions. Okay, for this to work, I mean, you have to make some assumptions about C. In particular, C itself has to be closed under compositions with AC0 computable functions. But again, all the complexity classes we were interested in have that property. Okay, so I told you it's an open question whether either of these has an effective syntax, and certainly an open question whether they have complete problems under AC0 reductions. Well, P and NP do. For NP intersect co-NP and for BPP, the existence of complete problems is open. If they did have complete problems, we would have an effective syntax. Okay. Actually, for these two, the converse is true as well. If you had an effective syntax, you could construct a complete problem. Okay. Again, sorry, that should be complement of LM bar. But I mean, I say under certain conditions, the converse is true. That is, under certain conditions, from a syntactic characterization, we can derive a complete problem. But you have to make, I mean, again, I don't have a general theorem along these lines because I don't have a general definition of what is a complexity class. Certainly true for NP intersect co-NP and for BPP, but there are complexity classes for which it's not true. Take PH, for instance, the polynomial hierarchy. We can give an effective syntax for PH, but there are, as far as we know, no complete problems. This is because the class contains an infinite hierarchy, and the existence of a complete problem would collapse the hierarchy down to a finite level. And polylogarithmic space is another class for which similar considerations apply. I mean, you can make you can make certain conditions explicit, which which will make the proof that works for these two go through. You can specify certain sufficient conditions and so on. So the general idea, I mean, I can just sort of one line proof idea is, say we had an effective syntax for BPP. So some enumeration of machine and polynomial pairs where this machine was guaranteed to be well formed, right, in the sense that every string is accepted with probability either less than 1/3 or greater than 2/3. Then you construct a complete problem by just considering triples of the form I, X, and then a string of ones, as just a string of symbols of length pi of the length of X. This is just sort of padding. And you consider the set of such triples such that the machine mi accepts X within that many steps. Okay. Now it's sort of fairly easy to see that any language in BPP can be reduced to this. It requires a lot more work to see that the reduction can be done in AC0, but pretty much, the I just codes which problem you're looking at. So you just translate X, put an I in front of it, take that pi, and put a sufficiently long string. So you map X to that string. Okay? If you want to reduce problem number I to this problem, you just map X to that particular string. And the thing is, the purpose of this padding is to ensure that the whole thing is still within the class BPP, because now this can be accepted by a machine whose running time is actually bounded by linearly in the length of the input, because you've just added this extra bit to the string to make it computable. And pretty much the same argument works for NP intersect co-NP as well. right? So from an effective enumeration, we can construct a complete problem. Okay. Now, I want to go back and talk about graph problems, right? I mentioned graph problems like connectedness, three-coloring, Hamiltonicity, etc. But when I started talking about complexity classes, the inputs were strings over the two-letter alphabet. So when we're talking about problems which take as inputs graphs, we need to express the graphs as strings, right? This is old syntax semantics distinction again. The graphs are our semantic structure. We need to write them down as bits of syntax. So the strings of zeros and ones, you just enumerate the adjacency matrix. I say the adjacency matrix, of course, given a graph. For any ordering of the vertices, I might get different adjacency matrix. And I said, if I'm given an n-vertex graph, there are up to n factorial different encodings of the same graph. Well, to be precise, it's n factorial divided by the size of the automorphism group of G. That's the precise number of distinct encodings. Okay. So let's say that two strings over the 0, 1 alphabet are equivalent if they are encodings of the same graph, right? In other words, if there is a graph for which one ordering of the vertices gives me the string x and another one gives me the string y. And let's say that a language L is invariant, let's call it graph invariant, if it's invariant under this equivalence relation. So whenever x is in L and x is equivalent to y, then y is in L as well.
So you mean the isomorphic graph?
Yeah. Yes.
Because it's semantic.
Exactly. Right. I mean, this equivalence relation is really, when people ask about deciding graph isomorphism, is just deciding this equivalence relation on strings. Okay. So now I'll define NP, or invariant NP, as the collection of all those languages in NP. Languages are sets of strings, which are invariant under this equivalence relation. And I describe invariant P as those languages in P which are invariant under this equivalence relation. Okay? In other words, they are actual semantic classes of graphs, right? Okay. Is this a syntactic class in NP? Well, its natural index set, if you will, is a set of pairs MP where M is a non-deterministic machine, P is a polynomial, and the language accepted by M when it's clocked by P is invariant. And as you see this and to the right of hand side, I've decided an undecidable semantic condition to my machines. And Fagin's theorem, the power of it is really, it tells us that nonetheless, there is a syntax for it. Right? The existential second order logic gives us a syntactic characterization of this class. So, in other words, the classes which are the translations of existential second order sentences, well, you know, take an existential second order sentence, you can translate it into a non-deterministic polynomial time machine, which evaluates that sentence on an input graph. That is necessarily invariant, and Fagin's theorem tells us you get all of them. Okay, that way. So Fagin's theorem tells us that this thing has an effective syntax. And now the open question of Chandra and Harel is really, is there an effective syntax for this thing over here, invariant P? Okay, so that's it. The open question by Chandra and Harel is there an effective syntax for this? Gurevich, in a paper in 1988, explicitly conjectured that the answer is no. Okay, and he gave this definition, which is really equivalent to what we've defined. So he didn't call it this. I mean, this is my notation. It has an effective syntax. If there's a recursive set and a Turing machine with the following properties, that on input I, M produces the code for a machine and a polynomial, right? If you run that machine clocked by PI, then it accepts a language that is invariant. And for every invariant language, there is a machine clocked by PI which accepts L. It's just the definition we've built up over the course of the lecture. That really is what appeared in Gurevich's paper. And he conjectured, as I said, that the answer is there is no such effective syntax. So now I just want to tell you, I'll mention a result. This was my contribution back in my PhD thesis, was to show that this thing has an effective syntax if and only if there are graph problems in P which are complete under first-order definable reductions. And the point about first-order definable reductions, right, reductions definable in first-order logic is they are AC0, so they're computationally very weak, and they're necessarily invariant, right, which AC0 reductions in general aren't. As I said, there are P-complete problems under AC0 reductions, even graph problems, but they're not under invariant reductions. Okay, you can't just say replace FO by AC0 sim-invariant reductions, because then your class of reductions is not necessarily enumerable, and so you can't go from the construction of the complete problem to a syntax. But it turns out that just considering first-order definable reductions is enough. And so the correspondence with the existence of a complete problem and the existence of an effective syntax goes through for this. Okay, that's what I wanted to tell you, but I just want to tell you, so the consequence of this result is, so we still don't know the answer. The open question, is there an effective syntax for invariant P, remains. But what this tells us is...
You mean graph problems in P?
Yes, there are graph problems. This should be P complete. That's the typo there. So basically, this tells us that one of the two things happens. Either there is no effective syntax for this in P, and consequences of that is there's basically no classification possible of polynomial time graph problems, right? Like you can't enumerate them all, you can't classify them all, and the way I like to think of it is there is an inexhaustible supply of efficient algorithmic techniques to be discovered, right? If we understand polynomial time as efficient algorithms, there'll always be new techniques, new methods to be discovered because you can't recursively enumerate them all. Another consequence of that, of course, is P is different from NP. So that's one possible world. Here's another possible world. There is an effective syntax. That implies that there's a P-complete problem under first-order reductions. And that means actually, far from being an inexhaustible supply, there is one holy grail out there of an efficient algorithm so that every polynomial time problem is an easy variation of that one algorithm. All right? Okay, I'll stop there.
A question.
Do I still have to stand and face the back?
Probably not.
Okay, it's the obvious question. So where's your money on out of those two possibilities? Or not you personally, but the people who think about these problems, do they believe either or?
Well, I mean, I don't know that there is a consensus. I mean, on that question, I'd say there is. I mean, I know there are dissenters, but there is a consensus in the community that P is probably different from NP. We just don't know how to prove it. We don't know how to prove real lower bounds, etc., etc. On this question, I would say I don't know that there is a consensus. I told you Gurevich explicitly conjectured that that's the case. Okay.
And does he still think so? I mean, that was in 1980.
Yes, I think if you asked him, he would still say so. But for instance, I think Neil Immerman has said he always thinks this is the more likely outcome. Okay.
And still P can be not that.
Yeah, and this is consistent with P is different from NP. Right? This doesn't imply a P. I mean, this is not. The point is this either or is not equivalent to the PNP question. It's
That's an oracle result then?
no. So this is the point is that.
I mean, how do you know it's consistent with?
Well, yeah, okay. I mean, consistent as far as we know is what.
No, but is there,
that was the form.
is there generalization
Yeah.
of the solvate theorem in an oracle? Can you separate, have P
Okay.
not equal NP and have the second thing happen?
No. Let me see. So if is there an oracle with respect to which P is different from NP, and there is an effective syntax for. I don't know actually. I don't know the answer to that one. What do I know? No, I'll have to think about that. I don't know.
So what's the basis of the intuition that you might have those three NP not equal NP? Other than you like those three and you think P is not.
No. Okay. So if P is different from, I mean, if P is equal to NP, then certainly you get an effective syntax for NP. But just assuming that P is different from NP, I have no, I guess I have no way of deriving that there isn't an effective syntax.
With the Oracle would do that.
But with an Oracle,
I would say that it's at least plausible that you could have P not equal NP.
Oracle, which concentrates on the isomorphism classes, but still on the actual sequences, it gives it's like having a definable well-ordering of the isomorphism classes of countable models, but not having a definable well-ordering on the reals.
Proof and see, can you make
okay, yeah. I mean, I think I'll have to think about that before. I don't think I can answer that question off the top of my head. Yeah.
Other questions? Well, if that's not the case, let's thank Anuj again.